Hello everybody. The lesson we're going to go over is limits. I think the best way to explain what a limit is by an example. In this case, let's consider x squared over x. It's plotted here on the right and it looks a lot like x. The only problem is there's a gaping hole right here at the center. If you look at 0, it's going to be 0 squared over 0, right? And you can't divide by 0. And if we plug in the numbers, as x approaches 0 from -1, you see it gets closer and closer to 0, right? As you approach it from the left side, you get closer and closer to 0. And as you approach it from the right side, you get closer and closer to 0. And so, therefore, the limit as x squared over x, as it approaches 0, is 0. And let me write it like this. Limit as x approaches 0 of x squared over x is equal to 0. Even though there's a hole, even though it is undefined at that point, we're interested in what the value to the left tends to and the values from the right tends to. So if you're following the function approaching the value towards 0, you see that it gets closer and closer to 0, and coming from the right side, it gets closer and closer to 0. And it's formally written like this, as I wrote earlier in the previous slide. One-sided limits. Sometimes you can't come from the left side. For example, here in our function, square root of x, it only comes from the right side. So if we're approaching it from the right side, it equals 0, right? But we can't come from the left side. Therefore, the limit as x approaches 0 of square root of x does not exist. Does not exist. Because you can't approach it from the left side. For a limit to exist, it must approach from the left and from the right side. Okay? And to signify that we are approaching from the right side, we use a plus sign here. And if we're approaching from the left side, then we would use a negative superscript in the limit there. Let's consider f of x is equal to x cubed minus 1. If we wanted to look at f of 3, you would just plug in 3 cubed minus 1. 3 cubed is 27. 27 minus 1. So then we know that f of 3 is equal to 26. Okay? So we can actually use direct substitution when we're taking limits. For example, when we take limit as x approaches 3 of x cubed minus 1 equal to 26, well, in the same way, we can just plug it right in. And if you look on the bottom here, as we approach 0, we get closer and closer to 26 here. And then from the right side, we get closer and closer to 26. Okay? But when do we have pitfalls in direct substitution? We divide by 0, and when we have infinity. So if you plug in and you get something divided by 0, some constant divided by 0, or you get infinity, that's where direct substitution does not work. Okay? So here's an example of a problem with direct substitution. If we plug in 2 here, 2 squared minus 4 all over 2 minus 2. 2 squared is 4 minus 4 all over 2 minus 2. we're going to get 0 over 0. Right? We can't do that. So there's a problem. So how do we fix it? There's 3 different techniques for solving for a limit. We can factor, we can expand and factor, and we can also multiply by the conjugate, which we'll cover later. Our first example, factoring, we can factor the top. So the limit as x approaches 2, x plus 2, x minus 2, all over x minus 2. Now we can cancel x minus 2 out. We don't care as the value of x at 2. We care what it is around it, right? So if we plugged in 3, any value other than 2, x minus 2 would cancel out. So now we're left with the value limit as x approaches 2 of x plus 2. And now we're not dividing by 0. We don't get infinity. We can just quickly plug it in. 2 plus 2. And that's equal to 4. Okay? Another technique is to expand and then factor. First, let's look at this. X approaches 0. Well, let's expand that. X plus 1, x plus 1 minus 1 all over x. So if we FOIL, right, we'll get x squared plus x plus 1 minus 1 all over x. Notice the 1 and the minus 1 cancels out, and then you're left with limit as x approaches 0 of x squared plus x all over x. Okay, we still can't plug it in because we're dividing by 0 in the denominator. So notice now we can factor the top. Limit as x approaches 0. Factoring the top, we'll get x plus 1 all over x. And again, because we don't care what the value is at 0, but everywhere around it, we can see that the x's can also cancel out. Now you're left with limit as x approaches 0 of x plus 1. And now we can simply just substitute it in. 0 plus 1 is equal to 1. And that's our answer. The next trick is multiplying by the conjugate. We normally have it when it has to do with a fraction that has some sort of square root in it. Okay? So this will be a little bit complicated. So a conjugate, let's say we have a plus b all over c plus d. Let's say we're trying to take the conjugate of c plus d, so we're going to multiply by c minus d all over c minus d. So that would be multiplying by the conjugate. Okay? In this case, we're going to be multiplying by the conjugate of the numerator. So the limit as x approaches 0, square root of x plus 4 minus 2 all over x. So we're going to multiply by the conjugate of the numerator. So x plus 4 So instead of a minus, we're going to do a plus 2. And remember, we have to multiply by the same thing, or else we're going to be changing the function, right? So in this effect, we're just multiplying by 1, which is perfectly legal. So we got limit as x approaches 0. Multiplying square root of x plus 4, we're going to get just x plus 4 because they're multiplying twice and they're inside the square root, right? So plus 2 square root of x plus 4 minus 2 square root of x plus 4 minus 4 all over. So I'm just going to leave it factored out, the x in the denominator, x plus 4 plus 2. The beauty of multiplying by the conjugate is that the middle term goes away. Now in the numerator, we don't have anything with a square root anymore. The 4's cancel out. So we're left with x over x square root of x plus 4 plus 2. And now the x's cancels out. So we're left with a 1 up top, square root of x plus 4 plus 2. Now we can directly substitute it in because we're not going to get the 0 in the denominator. So 1 over square root of 0 plus 4 plus 2 is equal to 1 over 2 plus 2. And then we get our answer 1 over 4. So a function can be defined as continuous if you can take any point in this function, approach from the left and from the right. The value of the limit, or the limit itself, is equal to the value of the function that's defined. When do limits not exist? For example, sometimes vertical asymptotes. For example, if you look at 0, as you approach from the right side, it goes to positive infinity. And as you approach from the left side, you go to negative infinity. So if you get negative infinity from the left and positive infinity from the right, it doesn't work out, right? Also, jump discontinuity. If you approach from the left, it's at -1. If you approach from the right, it's +1, so they don't agree, right? So the limit doesn't exist at 0 here as well. So here are some properties of limits. The first one, limit as a constant multiplied to a function is equal to that constant multiplied to the limit itself. So for example, in this case, limit as x approaches 1 of 3x, well, we can plug it right in. So we're going to get 3 times 1. Okay. And then on the right side, we're going to see that we'll leave 3 out top, and plugging in 1, we'll see that it's the same. It's 3 and 3. So you can evaluate the limit, pull the constant out of the limit from here to here, in that case, and then take the limit, might make things a little bit simpler. Also, if you're adding two functions, in this case f of x and g of x, and taking the limit of these two functions, you can take the limit of both of them and add them separately. Also, multiplying, if we're going to multiply two functions of x, it's the same thing as taking the limit of each function and then multiplying them together. Also, just like multiplying, we can do division. For example, limit as x approaches 0 of x plus 1 divided by the limit as x approaches 0 of x minus 1. Another example is if we're taking the limit of x approaches 2 of x plus 1 quantity squared, we can pull it out and just evaluate the limit as x approaches 2 of x plus 1 and then square it at the end. And in the same manner, the limit as x approaches a of square root of x, we can just take the limit of that function and then take the square root. For example, in this case, as x approaches 3 of square root of x plus 1, we can first take the limit as x approaches 3 of x plus 1, which is equal to 3 plus 1, which is equal to 4, and then we can take the square root. So then the square root of 4 is equal to 2. Okay? And that concludes the lesson on limits.